Imagine flying from Tampa to China, Australia, or anywhere else in less than an hour. Engineers at the University of Central Florida are working on the secret to safe hypersonic travel. For decades, humanity has dreamed of reaching the stars, but the vast distances between Earth and even the nearest stellar neighbors posed what seemed like an insurmountable challenge. Interstellar travel, long confined to the realm of science fiction, has been a tantalizing goal, one that seemed centuries away. But now, NASA has stunned the world with a groundbreaking announcement. The development of a light-speed engine capable of interstellar travel might finally be within reach. This revelation has sparked excitement, skepticism, and endless debate within the scientific community and beyond. What exactly is this light-speed engine? How does it work? And what does it mean for the future of humanity? To understand NASA's breakthrough, we first need to explore the challenges that have held us back and how scientists are overcoming them. The primary obstacle to interstellar travel lies in the distances involved. Our closest stellar neighbor, Proxima Centauri, is 4.24 light-years away. To put that into perspective, traveling to Proxima Centauri using our fastest spacecraft today, the Parker Solar Probe, which reaches speeds of about 430,000 miles per hour, would take over 6,700 years. Clearly, achieving interstellar travel requires a revolutionary leap in propulsion technology. Traditional rocket engines rely on chemical propulsion, burning fuel to produce thrust. While this method has been incredibly successful for launching satellites, exploring the moon, and reaching other planets in our solar system, it is fundamentally limited. Chemical rockets are constrained by the energy density of their fuel and the sheer mass of propellant required to sustain high speeds over long distances. To reach even a fraction of the speed of light, a rocket would need an astronomical amount of fuel, making chemical propulsion impractical for interstellar missions. Enter NASA's light-speed engine. Unlike conventional rockets, this engine leverages cutting-edge principles from theoretical physics and engineering to achieve speeds once thought impossible. Central to this breakthrough is the concept of propulsion without propellant, a radical departure from the methods used by all previous spacecraft. At the heart of this new engine is an advanced application of Einstein's theory of relativity. One of the most revolutionary aspects of relativity is the understanding that space and time are not static but can be bent, stretched, and warped. This insight forms the foundation of what NASA's researchers are calling the warp drive. The idea of a warp drive was popularized by science fiction, particularly Star Trek, but it has real scientific roots. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, describes a theoretical method of faster-than-light travel. Instead of propelling a spacecraft through space, the Alcubierre drive would compress space in front of the spacecraft and expand it behind. This creates a warp bubble that moves the spacecraft along with it. Within this bubble, the spacecraft remains stationary, avoiding the relativistic effects of traveling at the speed of light, such as time dilation. For decades, the Alcubierre drive was considered purely theoretical, as it required an exotic form of matter with negative energy density to create and sustain the warp bubble. This exotic matter, often referred to as negative mass, had never been observed in nature. However, recent advancements in quantum mechanics and material science have brought this concept closer to reality. NASA's breakthrough lies in their ability to generate a warp bubble using principles derived from quantum field theory. Scientists at NASA's Eagle Works laboratory, led by Dr. Harold White, have been experimenting with a phenomenon known as the Casimir effect. The Casimir effect occurs when two uncharged parallel plates are placed extremely close together in a vacuum, creating a negative energy density between them. By scaling up this effect and applying it in novel ways, researchers believe they can generate the negative energy required for a warp bubble. In addition to the Casimir effect, NASA is exploring the potential of quantum vacuum fluctuations. The quantum vacuum, often described as empty space, is not truly empty. Instead, it is teeming with virtual particles that pop in and out of existence. By manipulating these quantum fluctuations, scientists hope to create the conditions necessary for faster-than-light travel. The light-speed engine also incorporates advancements in plasma physics and electromagnetic propulsion. Plasma, the fourth state of matter, consists of charged particles that can be manipulated using electromagnetic fields. NASA has been developing plasma-based propulsion systems, such as the Variable Specific Impulse Magnetoplasma Rocket, VASIMR, which uses electromagnetic waves to heat and accelerate plasma. While VASIMR is not a warp drive, its principles have informed the design of the light-speed engine by demonstrating how to achieve high thrust without relying on traditional fuel. Another critical component of the light-speed engine is its energy source. To achieve the immense power required for faster-than-light travel, NASA is exploring the use of antimatter. When matter and antimatter collide, they annihilate each other, releasing pure energy. According to Einstein's famous equation, E=mc², even a small amount of antimatter can produce an enormous amount of energy, making it an ideal candidate for powering an interstellar spacecraft. However, antimatter is extremely rare and difficult to produce. Current methods of antimatter production, such as using particle accelerators, are expensive and inefficient. To address this challenge, NASA is collaborating with international partners and private companies to develop new techniques for antimatter generation and storage. One promising approach involves using magnetic fields to trap and contain antimatter particles, preventing them from coming into contact with matter. The implications of NASA's light-speed engine are staggering. For the first time in history, humanity could have the means to explore other star systems within a single lifetime. Imagine a mission to Proxima Centauri that takes just a few years instead of millennia. Such a breakthrough would open up a universe of possibilities, from studying exoplanets in detail to searching for extraterrestrial life. In addition to its scientific potential, the light-speed engine has profound implications for the future of humanity. Interstellar travel could provide a solution to some of the most pressing challenges facing our species, such as overpopulation and resource scarcity. By establishing colonies on habitable exoplanets, we could ensure the long-term survival of humanity and expand our horizons beyond the confines of Earth. Furthermore, the development of this technology could inspire a new era of international collaboration and innovation. Just as the Apollo program united people around the world during the space race, the pursuit of interstellar travel could bring nations together in a shared quest for knowledge and exploration. Of course, there are still significant hurdles to overcome. While the theoretical foundations of the light-speed engine are sound, its practical implementation requires overcoming immense engineering challenges. Building and testing a warp drive will require breakthroughs in materials science, quantum computing, and energy generation. It will also require significant investment and a long-term commitment from governments, private companies, and international organizations. There are also ethical considerations to address. As we venture into the cosmos, we must ensure that our exploration is conducted responsibly and sustainably. This includes respecting any forms of life we may encounter, as well as minimizing our impact on pristine extraterrestrial environments. Despite these challenges, the announcement of NASA's light-speed engine represents a turning point in our journey toward the stars. It is a testament to the power of human ingenuity and the enduring spirit of exploration. As we stand on the brink of a new era in space travel, we are reminded of the words of Carl Sagan. Somewhere, something incredible is waiting to be known. This is not just a story about technology or science. It is a story about our place in the universe and our collective potential as a species. With the light-speed engine, we are not just reaching for the stars. We are redefining what it means to be human. The journey ahead will be long and challenging, but it will also be filled with wonder, discovery, and the promise of a brighter future. The announcement of NASA's light-speed engine has sparked global fascination, but the journey toward achieving interstellar travel is far from complete. As we delve deeper into this groundbreaking technology, there are many aspects to explore, each raising new questions about how this achievement could reshape humanity's understanding of physics, engineering, and our role in the cosmos. The development of a light-speed engine is not a singular accomplishment, but the culmination of decades of research across multiple disciplines. To truly appreciate its significance, we must consider the broader context in which this revolutionary technology has emerged. The physics behind faster-than-light travel, at the core of NASA's light-speed engine, lies a fundamental challenge: overcoming the universal speed limit imposed by Einstein's theory of relativity. According to relativity, nothing with mass can travel at or faster than the speed of light in a vacuum, approximately 299,792 kilometers per second, 186,282 miles per second. The energy required to accelerate an object to light speed grows exponentially, approaching infinity as the object nears the speed of light. This limitation has shaped humanity's understanding of the universe and constrained our ambitions for interstellar exploration. But recent advances in quantum mechanics and theoretical physics suggest that faster-than-light travel may be possible if approached from a new perspective. NASA's light-speed engine sidesteps the relativistic barrier by leveraging the concept of space-time manipulation. By creating a warp bubble, the engine compresses space-time in front of the spacecraft and expands it behind, allowing the spacecraft to surf through space without breaking the light speed limit. This approach is consistent with Einstein's equations, which permit the warping of space-time under certain conditions. One of the most intriguing aspects of this technology is its reliance on negative energy. Negative energy, while counterintuitive, is a real phenomenon supported by experimental evidence. Evidence of negative energy is closely related to the concept of vacuum energy, which is the energy present in empty space due to quantum fluctuations. Harnessing negative energy on a sufficient scale to create a warp bubble represents one of the greatest challenges facing NASA's research. Recent breakthroughs in quantum field theory have provided new insights into how negative energy might be generated and sustained by exploiting the Casimir effect and other quantum phenomena. While scientists are making progress, translating these theoretical concepts into practical engineering solutions remains a monumental task. Building a light-speed engine is not just a theoretical challenge, but an engineering one. The materials, energy sources, and computational systems required for such a spacecraft are far beyond anything currently available. Yet progress is being made on multiple fronts. Advanced materials are essential for withstanding the extreme conditions required to generate and sustain a warp bubble. These materials must endure immense gravitational forces, extreme temperatures, and high levels of radiation. NASA and its partners are investing heavily in the development of metamaterials, engineered materials with properties not found in nature. Metamaterials can manipulate electromagnetic waves, making them ideal for applications in warp drive technology. One promising avenue of research involves graphene, a two-dimensional material composed of a single layer of carbon atoms arranged in a hexagonal lattice. Graphene is incredibly strong, lightweight, and conductive, making it a potential candidate for components of the light-speed engine. Energy generation and storage also pose significant challenges. The energy requirements for faster-than-light travel are staggering. To create and maintain a warp bubble, the spacecraft must generate an amount of energy comparable to the total energy output of a small star. Traditional energy sources, such as chemical fuels and solar panels, are wholly inadequate for this purpose. NASA is exploring advanced energy generation methods, including nuclear fusion and antimatter reactions. Fusion, the process that powers the sun, offers a nearly limitless source of energy by fusing light atomic nuclei into heavier ones. While fusion reactors are still in the experimental stage, significant progress has been made in recent years, bringing us closer to a viable energy source for interstellar travel. Antimatter, as previously mentioned, is another promising candidate. When matter and antimatter collide, they annihilate each other, releasing immense amounts of energy. However, producing, storing, and handling antimatter safely poses significant technical challenges. Quantum computing is also a critical component of the light-speed engine. The computational demands of a warp drive are immense. Controlling the warp bubble, navigating interstellar space, and ensuring the safety of the spacecraft and its crew require real-time processing of vast amounts of data. Quantum computers, which leverage the principles of quantum mechanics to perform calculations far beyond the capabilities of classical computers, are essential for meeting these demands. NASA is collaborating with quantum computing pioneers to develop algorithms and hardware capable of handling these challenges. Quantum computers could optimize the shape and stability of the warp bubble, predict and mitigate potential hazards, and enable autonomous decision-making during long-duration missions. The societal implications of interstellar travel are profound. The development of interstellar travel could usher in a new era of exploration, reminiscent of the Age of Discovery in the 15th and 16th centuries. Just as explorers like Columbus and Magellan expanded humanity's horizons, the first interstellar missions could open up an entirely new frontier. This era of exploration would not be limited to scientific discovery. It would have profound cultural, economic, and political implications. New industries could emerge around the construction and operation of interstellar spacecraft, creating jobs and driving innovation. Nations and organizations would compete and collaborate to claim their place among the stars. With great power comes great responsibility. The ability to reach other star systems carries a moral obligation to act responsibly. How should humanity interact with potential extraterrestrial civilizations? What measures should be taken to protect the environments of other planets? These questions demand careful consideration. The concept of planetary protection, which currently governs missions to other planets in our solar system, would need to be extended to interstellar exploration. This includes preventing biological contamination and ensuring that our activities do not harm native ecosystems. The pursuit of interstellar travel has the potential to unite humanity in a common goal. The challenges of building and operating a light-speed engine are so immense that no single nation or organization can tackle them alone. International collaboration will be essential, fostering a spirit of unity and shared purpose. This collaboration could extend beyond Earth. Imagine a future where humanity forms alliances with extraterrestrial civilizations, pooling knowledge and resources to explore the cosmos together. Such a scenario, while speculative, highlights the transformative potential of interstellar travel. As we look to the future, it is clear that NASA's Lightspeed engine is more than just a technological breakthrough. It is a symbol of humanity's enduring quest for knowledge and progress. While the road ahead is fraught with challenges, the rewards are immeasurable. Interstellar travel could fundamentally alter our understanding of the universe and our place within it. It could answer age-old questions about the existence of extraterrestrial life, the origins of the cosmos, and the nature of reality itself. It could also provide a solution to existential threats such as climate change, resource depletion, and planetary disasters by enabling humanity to establish colonies on other worlds. The journey to the stars will not be easy, but it will be worth it. As Carl Sagan once said, "The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself." With a light-speed engine, humanity is taking its first steps toward fulfilling this destiny. The future is closer than we think, and NASA's Lightspeed engine may be the key to answering that call. Are we ready to embrace the challenges and opportunities of interstellar travel? Only time will tell, but one thing is certain: the journey has already begun. The principle that currently guides space missions within our solar system is planetary protection. For example, NASA takes great care to sterilize spacecraft before sending them to Mars to avoid introducing Earth microbes that could interfere with the search for native life. With interstellar travel, planetary protection becomes even more critical. If we discover a habitable planet or one that harbors life, how do we ensure that our presence doesn't disrupt its ecosystem? Could the introduction of Earth organisms lead to the extinction of native species, much as invasive species have wreaked havoc on Earth's ecosystems? Some scientists argue that humanity has a moral obligation to avoid interfering with alien life, even if it is microbial. Others contend that exploration and colonization are inevitable and that we should focus on minimizing harm rather than avoiding it altogether. The possibility of encountering intelligent extraterrestrial life raises even more complex ethical questions. How should humanity approach first contact? What protocols should guide our interactions? Should we attempt to communicate, or should we observe from a distance? Many scientists and philosophers caution against broadcasting our presence to the cosmos. They point out that we have no way of knowing whether alien civilizations would be friendly or hostile. Others argue that the benefits of communication, such as the exchange of knowledge and culture, outweigh the risks. First contact could also force humanity to grapple with questions of representation. Who speaks for Earth? Would individual nations or organizations attempt to establish their own relationships with extraterrestrial civilizations, or would humanity present a unified front? If humanity discovers a habitable planet devoid of intelligent life, the temptation to colonize it may be overwhelming. However, colonization carries its own ethical dilemmas. How do we ensure that colonization efforts are equitable and inclusive? How do we prevent the exploitation of these new worlds for the benefit of a few at the expense of the many? These questions are particularly pressing in light of humanity's history of colonization on Earth, which has often been marked by violence, exploitation, and environmental destruction. To avoid repeating these mistakes, interstellar colonization efforts would need to be guided by principles of sustainability, justice, and respect for the intrinsic value of other worlds. The announcement of NASA's Lightspeed engine is a monumental milestone, but it is just the beginning. The journey from concept to reality will likely take decades, requiring sustained investment, collaboration, and innovation. One of the first steps in bringing the Lightspeed engine to life is rigorous testing. This involves not only validating the theoretical principles behind the technology, but also demonstrating its feasibility in controlled experiments. NASA scientists are already working on small-scale prototypes to test the basic components of the engine. One of the biggest challenges is scaling up these prototypes to a size and power level suitable for interstellar travel. This will require breakthroughs in materials science, energy generation, and computational modeling. Given the immense complexity and cost of developing a light-speed engine, international collaboration will be essential. NASA is already working with space agencies, universities, and private companies around the world to pool resources and expertise. Such collaboration could also help ensure that the benefits of interstellar travel are shared equitably. By involving a diverse range of stakeholders, humanity can work toward a future where interstellar exploration is a collective endeavor rather than a competition. The success of a light-speed engine depends not only on scientific and technical achievements, but also on public support. NASA and its partners will need to engage with the public to build enthusiasm and understanding for the project. This includes addressing concerns about the risks and costs of interstellar travel, as well as highlighting its potential benefits. Public engagement is also crucial for inspiring the next generation of scientists, engineers, and explorers. Programs that encourage young people to pursue careers in STEM fields will be vital for sustaining the momentum of interstellar research. Once the Lightspeed engine becomes operational, the possibilities for interstellar missions are virtually limitless. Here are just a few of the scenarios that scientists and science fiction writers alike have envisioned. One of the most compelling reasons for interstellar travel is the search for life. With a light-speed engine, humanity could explore exoplanets in the habitable zones of nearby star systems, such as Proxima Centauri, Alpha Centauri, and TRAPPIST-1. These missions could involve sending robotic probes to survey the planet's surfaces, atmospheres, and potential biospheres. If signs of life are detected, follow-up missions could be launched to study these findings in greater detail. The discovery of a habitable planet could also pave the way for humanity's first interstellar colony. Such a mission would require the development of massive generation ships capable of carrying thousands of people, along with the infrastructure needed to establish a self-sustaining settlement. Colonization missions would likely be preceded by extensive reconnaissance to assess the planet's suitability and identify potential risks. These missions could also involve terraforming efforts to make the planet more hospitable for human life. The Lightspeed engine could also enable humanity to explore the farthest reaches of the galaxy. Missions to study black holes, neutron stars, and other extreme cosmic phenomena could provide new insights into the fundamental nature of the universe. These missions would not only advance our understanding of astrophysics, but also inspire new technologies and innovations. For example, the study of black holes could lead to breakthroughs in energy generation or quantum computing.